Sometimes the MUX or the multiplexer is also called as a universal gate. The reason is because using a MUX we can create a NOT gate, an AND gate, an OR gate, or an XOR gate. Let us see how we can do that. So using a MUX, let's create the NOT function. So this is a procedure. You know that for a NOT gate, f is equals to a prime, right? So when a is 0, f is 1, and when a is 1, f is 0. So to realize this, let's draw the MUX. It has two ports, 0 and 1. It's a 2 to 1 MUX. And the way you want to solve this is, the select is going to be A. Okay? Now when A is 0, that is, we automatically go to the 0 port. F is 1. So when A is 0, F is 1, which is when this happens. And similarly, when A is 1, you select the 1 port. Your output should be a 0. Therefore, you put a logic 0 as the input. And this is going to get satisfied by this. So when, let's say, A is 0, so you select the 0 port, and then F is equals to 1. And similarly, when A is 1, you select the 1 port, and the input for the 1 port is 0, so you get F equals to 0. So that's how we can get the NOT functionality using a MUX. Now let's go for the AND function. So for the AND function, we know that f equals to a and b, right? So when a is 0, f is automatically equal to 0. And when a equals to 1, f depends on b. So f is equals to b. If b is a 0, your f is a 0. If b is a 1, then f is a 1. So let's construct the 2 to 1 MUX. We have 0 port and the 1 port, and we're going to take a as the select line and f. So here we have, when a is 0, f is equals to 0. So when a is 0, the 0 port is selected, and the only way that the output is going to be a 0 if we give it a 0. Similarly, when a is 1, f depends on b. So when a is 1, the 1 port is selected, and your output depends on b, therefore we just write a b. So that's how you can make an AND function using a MUX. Let's go for MUX to OR function. So you know that for OR, f equals a plus b. So when a is 0, then f is equal to b. It depends on b. So if a is 0 and b is 0, then f is also 0. If a is 0 and b is 1, then f is a 1. Therefore, f depends on b. And when a is 1, your f is automatically 1. You do not worry about the value of b in that case. So let's make the MUX 2 to 1, 0, 1, f, select is a. So when a is 0, f is equals to b. Therefore, connect b to the 0 port. And when a is 1, f is automatically 1. Therefore, connect logic 1 to the 1 port. And that's how you can realize an OR function using a MUX. Let's go for the final one, which is MUX to your XOR gate. or your XOR function. Now if you remember, the XOR function is A prime B or AB prime. Okay, so when A equals to 0, this term gets cancelled out, this term remains. In that case, when A is 0, F depends on B, so F is equals to B. And when A is 1, which means this term gets cancelled out, this term is going to remain. F depends on B prime. So to construct your MUX, take 0 port, 1 port, select is A, output is F. When A is 0, F depends on B. So connect B to the 0 port. And when A is 1, F is B prime. So connect B prime to port 1. And this is how you can realize an XOR function using a 2-to-1 MUX. Hence, your MUX is also a universal gate.